Hello and welcome back. We said that there was something called as evolutionary computing, which had of course a lot of potential in itself, which had got a lot of power in not only just optimizing, but as we call as evolving systems, in what is sometimes called as learning in systems. And they not only taken a fitness function that they optimize, but rather they are able to make machines, they are able to make in systems, they are able to make in solutions to problems, and they may be as less limitation as possible, they may be as less constraints as possible in design, in conceptualization of this problem. And what we see is that an incredible potential of these algorithms to solve some really good real-life applications. What we said that evolutionary computing consists of the genetic programming, the evolutionary programming, the genetic algorithms that we saw first of all, and the evolutionary strategies. We saw how each one of them worked, which was more or less on the same lines, which was more or less on exactly the same lines as the other algorithms work, and based on some different amount of phenomena, based on some different amount of adaptation from the general evolutionary computing algorithm, we saw that we generated the different invariants of the evolutionary computing algorithms. We studied all the various invariants. So once the basic genetic algorithm and the general properties of evolutionary computing is discussed, most of the discussion, be it any evolutionary computing technique, that happens to be quite very the same. And today we'll continue the same discussion, wherein we'll have a look into the last fundamental pillar of the evolutionary computing. We'll have a discussion over the last pillar of this evolutionary computing, that is known as evolutionary strategies. The very fundamental of evolutionary strategies again says that because it's evolutionary in nature, so I'll have in a pool of solutions to a problem what is called as the individual. I'll have this individual pool with me. What this individual pool will do is that it will interact with itself. The various individuals will interact to form in a next potential generation of population based on my understanding of the previous generation as well as the future generation, based on my understanding of the past and the present and the newly generated individuals. I'll make in what I call it as my next generation of population, and this process will go on and on and on, wherein every old generation individuals, they'll do something, and based on the newly generated individual and the old individuals, I'll make my next generation of population. I'll select my next generation of population, and as we saw in genetic algorithm and genetic programming, that the best in fitness, it keeps on increases along with time. The best fitness will keep on increasing. What we said was that the fitness value of the best individual on the average fitness value, sometimes even the worst fitness value, it keeps on increasing along with time, until and unless all individuals, they almost kind of converge to some kind of place, and after that there is some kind of exploration, and in that manner we say that the algorithm was potentially trying to locate the global minima and trying to escape all from the various local minima. So that's about the evolution. Here again, we'll of course have in a technique to represent the individual. Now the technique used to represent the individual over here in this evolutionary strategies is that the entire individual, as in the genetic algorithm it follows, So I'll have some x1 over here and x2 over here and x3 over here, x4 over here and some xn over here. This is exactly the individual of the genetic algorithm that is embedded right inside here. But because the word is strategies, so I'll have some extra things added to this individual. Because the fundamental domain, the fundamental concept used is known as strategies, therefore I'll be adding in something extra to this individual, and whatever extra I add to this individual somewhere over here is known as the strategy parameters. Or let me say the strategy variables. So there are some individual representation variables, and there are some extra variables that are added to this individual. There are some extra kind of variables added to the system, and those are what are known as the strategy variables. These strategy variables, as we shall see later, would be of two types. These are the first strategy variables. And these are the second strategy variables. These represent some kind of mutation strength, as we shall see later, and these represent some kind of rotation over the fitness landscape. That is what we shall see later. There are some rotational and there are some mutational parameters that are added. But for an initial discussion, what we have done is that we have added some kind of extra variables to this individual. We have added some new kind of variables over here, and these variables are what are known as the strategy variables. So my entire individual consists of some variables that help me determine what the phenotypic representation would be. If it's optimization of a neural network, it means that this represents a neural network where there are some various weights, there are some various biases applied over here. If it is the evolution of intelligent system that solves the problem of face recognition, all those parameters would come up over here. So this is what is the problem definition part of it. These variables help me determine the problem, and there are some extra variables. What these variables denote the strategy with which the evolution will take place. The strategy variables are the variables that represent, that denote the kind of strategy by which the evolution will take place, and hence how the evolution is to be carried out. How the entire evolution is to take place is an information that is embedded along in the individual as well. It has been embedded into the individual, and when I say it has been embedded with the individual, multiple individuals will have multiple strategy parameters. All the multiple individuals will have multiple strategy parameters which will eventually change along with time. All the strategy parameters will change along with time, and hence the entire evolution, it decides on its own how the optimization of this problem needs to take place. These are the parameters that determine how the evolution of this part of the problem needs to take place. And since it's a genetic individual, everything changes along with time. So the strategy keeps on modifying itself. It keeps on changing along with time as per situation demands, and that is what we have as the term adaptation. So that is what we have as the term adaptation. What adaptation into our initial discussion it denoted was that all the crossover rate, the mutation rate, and all these things need to change along with time. They need to take their optimal values along with time, so that the evolution is directed in a best possible mechanism. So that the evolution is directed in the very best possible mechanism, And that is something that we are trying to do out over here, Now this term adaptation has multiple attempts that has been given by multiple people across. There have been multiple events that multiple kind of possibilities that people have tried to explore. One of the very initial ones comes from Reichenbach, which is known as Reichenbach 1/5 principle. That was an initial attempt to make the genetic algorithm more adaptive in nature. That was an initial attempt that stated how can we make the genetic algorithm more and more adaptive in nature. So what this principle said is that if the successful mutations happen to be less than 1/5, that means that all the mutations they are producing very bad mutation values, then we need to decrease in the mutation rate, and therefore we decrease the mutation rate by an amount of 1/5. We decrease the mutation rate by a degree by an amount of 1/5. And if suppose the total number of successful mutations are fair enough, they are high enough, then we increase the mutation strength by an amount of 1/5. So that is what Reichenbach, after studying the successful mutations or these unsuccessful mutations, he was able to adapt the kind of mutation that an algorithm should have, the kind of mutation value should have, and hence when using this principle, when we go about evolving our system, our mutation strength keeps on increasing and decreasing. The successful mutations are an indicator of whether the mutation strength should be increased or it should be decreased. Now remember, if the mutation strength is too low, my exploratory nature is very bad in nature. I almost try out nothing new, and the next individual generated will be almost similar to my own individual. And hence what will happen out is that the convergence will be very slow. Or the exploration will be very slow. All the individuals act as nothing but like agents out in the fitness landscape, and mutation rate denotes with what speed are they walking in this fitness landscape. And if the mutation rate is very slow, their step size is very slow, they are walking at a very low rate, they are walking at a very low pace. And since they are walking at a very low pace, at a very low rate, what happens out to be is that my algorithm behaves very slow in nature, and of course if the mutation rate is very high, you can expect that there will be no convergence at all. The algorithm, all these individuals, they keep on hopping towards around some kind of minima, and they will ultimately not converge deep inside. So the final optimal value that I get would be very vague, it will not be good in nature. So based on that, low mutation rate is bad, a high mutation rate is bad. So Reichenbach stated, how can we adapt this mutation rate where based on some principle the rate is adapted, the rate is modified in a way that the algorithms behaves even better in nature. I use the term as successful mutation over here. Now this is an important term over here, since it is used as an indicator to how the mutation rate should be changed. A successful mutation means that there was an individual, I applied some kind of mutation over it, and the fitness value improved. There was an individual, I applied some kind of operator over it, I applied some kind of fundamental over it, I applied some kind of operation over it, called as mutation, and the fitness value improved. So after application of mutation, if this fitness value improves, if after application of mutation, the fitness value increases, then I state that my mutation is successful. If by chance my mutation is applied to an individual and the fitness value in place of improving, it decreases. If my fitness value decreases, then I call my mutation as an unsuccessful mutation. At any point of time, I have got multiple individuals on which this mutation operator is applied. I've got numerous individuals over which this mutation operator is applied, and hence some of the applied mutations would be successful in nature and the others would be unsuccessful in nature. Some of the operations would result in a successful individual and the other operations would result in an unsuccessful individual. So based on that, I measure out the total percentage of mutations that were successful in nature and the total percentage of mutations that were unsuccessful in nature. And if the number of successful mutations is low, less than 1/5, then is when the mutation value is increased by an amount of 1/5 of its total value. So this is one of the attempt in which I can adapt the mutation rate. Evolutionary strategies is nothing but some kind of enhancement or some kind of reputed enhancement wherein we do not use this general principle, general guidelines, but rather we embed some kind of strategy over the individual itself. And by this very embedding of strategy inside this individual, we are able to obtain a high amount of fitness. We are able to obtain a high amount of value of fitness, and as a result, we are able to get much better convergence, much better value of the final fit operation, and hence the effectiveness of the algorithm should generally increase. The effectiveness should generally increase, apart from the fact that of course I've added in some new kind of variables over here that would increase the individual size. The other thing is that these are some strategy parameters that are added. Now from the discussion so far, what we realize is that the main adaptation that needs to be done is in the crossover or is in the mutation operator, as that is the main factor that decides how the evolution should take place. The crossover operator is more or less conventional in nature, which does nothing but making the individual jump towards better places by an exchange of characteristics. So there is very little we can do over it, but what the main thing that we need to do, what is the main thing that we need to ideally carry out is the fact that how do we adapt the mutation rate. If we are able to adapt our mutation rate, then we would be able to get an adaptive system possible. In case of evolutionary strategy, it's called as a self-adaptive system possible, where everything is inside the self, where everything is inside the individual itself. If we are able to get this kind of system possible, then the mutation rate will keep on modifying, and that will benefit the entire individual, the entire algorithm. So these are what are known as a strategy parameter. The number of parameter is equal to n sigma plus n alpha. Of course, these are one type of strategy parameters, these are the other type of strategy parameters, both of which are used to decide only one thing, and that is the mutation rate. Both these strategy parameters, they only decide with what mutation rate all these bits over here, all these real numbers over here, they are to be modified. With what mutation rate they are to be modified. These are the strategy parameters that carry out this task. Now normally there is a relation between n, the total size over here, and n sigma, the total size over here, and n alpha, that is the total size over here. There is some kind of relationship over here, and that is what we get when we study how internally these are applied. That is what we will see much later into the lecture of how these all are formalized. but what would come out to be is a general relationship, and of course these are based on whatever mathematics we would apply later and how we will calculate defining mutation rate based on these strategy parameters, when we will see how this comes out to be, how does the science comes out to be. But there is a relationship between all these three fundamental entities, the n alpha, n sigma, and the n, that is the individual size over here. So based on that, if I know this, I can calculate what my entire individual would be, and then the entire evolutionary algorithm can continue. We'll look in a little deeper into the algorithm. Now, because it is entirely an evolutionary algorithm, the general guidelines are the same, that we generate random population. We'll generate some kind of population which is nothing but some kind of individuals. We'll generate all these individuals up. After the generation of these individuals, this population, what we'll do is that we'll continue in a loop. So while stopping criterion is not met, we'll have in a population, we'll do some kind of selection, again more or less this same genetic algorithm that continues. We'll do a crossover, what is sometimes called as a recombination. When it comes to the fundamental principle of the evolution strategies, we have it terminalized as a recombination. Of course, there is a mutation, and this is what is the most special operator when it comes to the evolution strategies. This is what happens to be the most fundamental operator, wherein the mutation, it denotes how the exploration in a fitness landscape takes place. All these strategy parameters were embedded into the individual only to have a good mutation. I will of course have in some fitness evaluation, and then I'll have something that is where I form the next generation. And then this algorithm would go on and on. So more or less the standard genetic algorithm, except for some slightly different term of recombination used. The other concept is of course that I have an extra term wherein I formulate the next generation that was not necessarily extrinsically written out in a genetic algorithm. What happens in an evolutionary strategy is there is a population P out over here at any time t. Based on the operators recombination and commutation, I happen to get in my higher generation of population P dash T plus 1. Now this is not given to the higher generation as it is, but rather sometimes what we do is that we look at in these individuals out over here, we look at these individuals out over here, and based on all these individuals, we select the best few individuals here, and that is what exactly is the next generation population. So the population of the next generation may not necessarily be formed by the operations of recombination and mutation into your old generation to generate a new generation. It may not necessarily be formed as it is from the old generation to the new generation. Rather, we use all the evolutionary operators to generate in a pool of individual, and then both the parents and the children, they compete. Then there would be a competition, there would be a survival of fittest, there would be a struggle for fitness amongst the parents and the children, and a collection of both the parents and children would be taken. So if these are the parents, these are the children, a collection of both of which would be taken. And what we'll do is that we'll select out the best individuals from this selection pool. From this pool, we'll select out the best individual, and that is what will formulate the next generation of population. So that is what is the generation of next generation from a lower generation in the evolution strategies. Of course, sometimes we carry forward the same simple task, is that Our parents, they are children, and we take this out to be the actual population of the next generation. So there is no competition between the parents and children. This is also something that is applied, as we shall see later. So that's what the general evolutionary strategies, the algorithm is all about. Now the evolutionary strategies, we've got an interesting notation by which we can denote an evolutionary strategies. We can always denote it by some good, short and compact representation, and that is what we call it as the representation of evolutionary strategies. Remember, it's not the representation of individuals in evolutionary strategies, but rather whatever strategy that you are applying, how do you represent it so that as a mathematical expression you can denote it. The simplest evolutionary strategy that is possible is called as the 1+1 evolutionary strategy. The simplest evolutionary strategy that is possible is called as 1+1 evolutionary strategy. And what a 1+1 evolutionary strategy means is that there is always one individual in population pool. There is always a single individual in the population pool. So my multi-agent is like almost gone. Now it's a uni-agent system and comprises of only one individual. And remember that when we were dealing with the genetic algorithm, we've got the bulk of individuals, we had all complex parameters. Evolution strategy seems much more simpler than that. We are even talking about a single individual inside it. Of course, the multi-agent we will see immediately after it. The evolution strategies, they always seem to be much more simple in nature as compared to the conventional genetic algorithm. They seem to be much more simple in nature, not complex but much more simple in nature, where we even talk about the single individual, and that's again attributed to the adaptive parts of these algorithms. So what this denotes is that there is only one individual in the population pool. There are some genetic operators applied over it and it generates exactly one child. So at any generation, this one individual will generate one child. So it's like one parent and that gives us one child. We make it a pool of both these individuals, so we get one parent plus one child, that is equals to two individuals. We get in some two individuals over here, one parent and one child. We select the best out of these two individuals. We select the best out of these two individuals, and that is what gives us the next generation population. We select exactly one individual over here, and that is what gives us the next individual or the next generation population. So at any time I have only one individual, I apply something, I generate in a child, see which one is better, the better one survives. I again do something over it, it changes its forms, it generates in a child, I see, look at which one of them are better, of the parent or the child. I keep the better one, this becomes a parent now, I again do something out over here, I generate it's one of its child. I again see which one is better out of the parent and child. So one individual, it keeps on hopping between generations. One individual, it keeps on going between generations, and that is how this entire algorithm goes. That's how this entire algorithm goes. This is what is known as a 1+1 evolutionary strategy. And of course, this is like the most simple part of the simple evolutionary strategies that is possible, the 1+1 evolutionary strategies. I'll generalize this thing up to what is known as a lambda plus mu evolutionary strategy. There's a second representation that we would be dealing with, known as a lambda plus mu evolutionary strategy. In this kind of strategy, what happens is that my population pool, it contains lambda individuals. My entire population pool will consist of some lambda number of individuals. So I've got lambda individuals up over here. I apply some kind of operators over here and I'll generate mu children. Now whenever we dealt with genetic algorithm, we never dealt with how many parents and how many children, as we know that n parents always generate n children, and therefore things are very easy for us. We know that if there are 100 parents, there will be 100 children. If there are 200 parents, there will be 200 children, and so on. Here we are differentiating between the number of individuals in the parents and the number of individuals in the children. And that's again what can be seen from natural world. It's not necessarily that each couple of parents generates a couple of children. We can have any way possible. Many parents generating in one child, or many parents generating a still higher number of children, and so on. So out here at this evolutionary strategy, we take this phenomena into account, where the number of parents is not necessarily equal to the number of children. They can change. There can be a change between the number of parents as well as the number of children out over here. So this is what is known as a lambda mu evolutionary strategy. All I have is a population pool of lambda individuals. So at any generation, I have to generate the next generation population from the previous generation population. My previous generation population has exactly lambda individuals, and I need to generate the next generation population. The next generation population will again contain of lambda individuals. So how do I generate that? The mechanism by which I generate that, I first of all generate from lambda parents. I carry out some kind of operation over lambda parents and I generate mu children. From these lambda parents, the previous generation population that serves as the parents, from these parents I generate out some children. So if they are lambda parents, I generate out mu children out over here. I make in a population pool that contains lambda parents, mu children that are just formed. These are already there with the population. In all lambda plus mu individuals, I make in this population pool and I select the best lambda, and that is my population for next generation. That is what becomes my population for the next amount of generation, wherein some parents are forming where there are some parents and some children, and together what they are forming is the collection of parents and children. The parents and children, they compete with each other, and when there is a competition between the parents on one part and the children on the other part, these compete and they generate in the next generation population. They generate in the next generation of population, and this next generation of population is what repeats itself. Of course, when I say they generate new children, I mean that both the recombination and the mutation operator has been applied, and after these recombination and mutation operator, I get the children. So after I get the next generation population, I apply the same fundamental principle where lambda parents of the next generation now, they generate new children. The parents and children, they compete with each other and they form in, I'll make in a population pool, I'll select the best lambda individuals and they form a still higher level of generation. They form a still higher level of population, and this higher level of population is exactly how this loop goes on and on. This loop, it keeps on repeating with itself. And that is how the entire evolution is carried out when I deal with the evolutionary strategies. This is how the entire loop that happens, it takes place. So that is what is known as a lambda plus mu evolutionary strategies. I'll keep the same notation, I'll keep exactly the same notation, but represent it as lambda by rho plus mu evolutionary strategies. I'll apply it out over here as lambda by rho plus mu evolution strategies. So here also the population pool, it contains some lambda individuals. So there are some lambda individuals in the population pool. So there are some lambda parents out over here. What they form is mu children. The only difference between the two is how this formation takes place. Now this formation would be by the application of recombination and mutation operator. In evolutionary strategies, what we have is that if there is a population pool, I apply a recombination operator, get the population pool, then I apply a mutation operator and get the children. So this forms the parents, this forms the children. Mutation is individual specific, so there are new children out over here, there will be new individual out over here, and there are lambda individuals over here. So there are lambda parents. After recombination, they generate new children, and these new children, they undergo mutation and again generate new children. So the only difference is in how do I apply the recombination between the two evolutionary strategies. A lambda by rho evolutionary strategies. A lambda by rho notation of the evolutionary strategies. What it says is that for making in these children out of these parents, I'll group rho parents. So I'll generate in a pool where there will be rho parents. So there will be a parent 1, there will be a parent 2, and there will be a parent rho out over here. And these are what will generate out the children. So this is a multi-parent recombination that takes place in a mu by rho plus in a lambda by rho plus mu evolution strategies. There is a multi-parent. There is a multi-parent individual recombination that takes place in these types of evolution strategies, where I make a combination of rho parents. I make a combination of rho parents, and these rho parents are ultimately that generate in a child. These rho parents take together generate in a child. So the child has got a characteristics of all these rho parents. It gets some characteristics from some parent. It gets some characteristics from some other parent, and in totality it contains in all these kinds of characteristics that come from all the various kinds of parents. So that is what is known as a lambda by rho plus mu evolutionary strategies. Now one thing important to notice out over here is that suppose there is an individual that is very fit. I take in X as a very fit individual. I take in X as an individual that suppose is very fit in nature. Now this individual out over here, because it has a very high value of fitness, it will participate more in nature and generate in children. Now in evolutionary strategies, unlike genetic algorithm, what happens is that the children and the parent, they compete with each other, and because X is very fit, therefore these are chances that it gets selected for the next generation, and it goes up to the next generation. So if X was generated at generation T, this was the generation at which X was generated, there are more or less chances that it will go to the generation T plus 1 as well. And why will it go for T plus 1 generation as well? Because it was very fit, so when compared with the children, it had got a high degree of fitness value, and therefore when we select the best lambda individuals, it goes to the next generation as it is. The other, of course, important factor is that it's going as it is to the next generation. There is no recombination applied over it, there is no mutation applied over it. Of course, these two operators were applied to generate the children, but the parent remains intact, it remains unchanged. And when it goes from generation T to generation T plus 1, we say its age is 1. It has got an age of 1 generation. Similarly, it's at generation T plus 1, it will generate a good amount of individuals, it will generate in some high values of individuals. they might have a better fitness, they might have a worse fitness, but because X is already fit, it might go to the generation T+2 as well. It went to generation T+1, it might go to generation T+2 as well, because of the fact that it may have in fitness that is amongst the best lambda fitness over here, and that is when we say that the age is 2. So any individual of evolutionary strategies, it has got an age assigned to it. Every individual has got some age. Age denotes the number of generations for which this individual is alive. It denotes the number of generations for which this individual is alive. If an individual is very fit, exceptionally fit as compared to the other individuals, if it's almost at the global minima or the global maxima in terms of cost or the fitness landscape, then what happens is that it will have a very high age, because the entire evolutionary strategies will have to generate in lambda individuals that have got a higher fitness value as compared to this. And once it does so, once it generates in lambda individuals of a higher fitness value as compared to this individual, then it's only that this individual is not selected for the next generation. Else it will keep on getting selected from one generation to the other generation, from the other generation to the third generation. And only reason why this is happening is because I had made in parents to compete with the children to generate in the next generation of population. Because there was a competition between the parents and the children, that is why this age factor has come into the picture. If you apply the same factor for the genetic algorithms, it will come out to be 1. The maximum age will come out to be 1. Of course, there is elite operator which may give some age, but application of elite operator to an individual, we say that even though the child is exactly same as parent, but it's a new child. So that's what is the age parameter. So every individual will have some age, and that means every individual will be born and it may die. Many times individuals, they do not die at all. They keep on getting selected again and again and again and again and again, and after that there is a stopping criterion that is met based on fitness value, based on the individual slack time, based on slack generation or any other factor, and hence individuals may die, but all of them they are born and they have an age, even though the age may be 1. If I apply some kind of operations and the generated individual happens to be very bad in terms of fitness, then it dies immediately, else it may die at a later stage of time. So that is what was known as a lambda by rho plus mu evolutionary strategies. I'll apply again a small addition to it. I'll again say lambda by rho plus mu evolutionary strategies, except for taking in a bracket over here, I write down comma k. Now what happens when an individual has an exceptionally large lifetime? Lifetime is again age. So what happens when an individual has gotten a very high degree of age is that there is a premature convergence. Now this individual is occupying one valuable position at every generation. So as a result, I have in the effective individuals that go from the previous generation to the past generation much less. And if it happens for multiple generations, what happens is that my one individual is keeping its kind of waste. I need to always transfer it from the previous generation to the past generation, and it keeps on attracting individuals as well. So sometimes I say that the maximum that this individual can contribute in its lifetime is what I will be able to get in k generations. After that, I will not allow it to populate more characteristics into this generation, into this population pool, because it is known that if this every fit individual, it keeps on sharing its characteristics with the other individuals. In this strategy, we fix in a maximum lifetime. We say after this lifetime, the individual will not be allowed to live, it will be dead. It will be forced to be dead. And why do we kill an individual in an evolutionary strategy? That is when we say that it has contributed enough characteristics to the population pool. Keeping it alive for more generations will make the individuals converge towards the same point in which this individual lies. And if it converges towards this individual lies, these points were already known in nature. These points were already known in nature, and hence the exploration goes away. The exploration path goes away. Now remember, even when there was a kind of convergence into the genetic algorithm and we had some generations left, if there was some kind of convergence that happened and we had some generation left, we try to increase the mutation value. We try to increase the mutation value to enhance exploration to a population that had already converged at some point of time. That is why deleting this individual is important. And hence we say that maximum lifetime of an individual is K. So we take in lambda parents, we take in mu children, we apply a lambda plus mu individual, we take in the best out of this to generate in lambda individuals for the next population. But while making this selection, we make sure that none over here it crosses an age of K. None of the individual over here should be crossing out an age of K. Now suppose any individual crosses out an age of K, no matter it may occupy in a very high amount of fitness, no matter it may be enjoying a very high amount of fitness, but we do not take it at the next generation, we make it die out over here as well. Now we'll keep again taking the same representations that we had taken so far apart from a change. So let me say lambda rho mu out over here, and I use the word comma out over here. Now the populations that I had written a lambda by rho mu, sometimes they also referred by this where there is a comma appended to the plus. Comma is just a separator, and plus denotes that I am taking in parents plus children. I am taking in this, I am conducting parents as well as children for deciding the next generation population, that is what the plus denotes. So here there is no plus and only a separator has been used. Here there is no plus and only a separator has been used. So the only difference between these two strategies, the only difference between the two evolutionary strategies is the fact that I have got rid of plus over here. The only difference between these two representations is that I have got rid of plus over here, and hence in this what happens is that again there would be lambda parents, that is will be equal to my population size. I'll apply some kind of technique to generate new children, but here what would happen is that there is no plus, so there is no competition between the parents and the children, and as based on only the children I select the best lambda individuals out here and they become my lambda parents for the next generation. So there is no population pool will consist of only children, not the parents, and that goes for say that mu must always be greater than lambda or equal to lambda. If it's less than lambda, I will not be able to select the best out of them. I'll have only mu solution, but I have to generate a larger number. I'll select a larger number of individuals, so that won't be possible. So mu has to be greater than lambda. But what ultimately is the case is that I select the best lambda out of this population pool that comprises of only the children and not the parents. So there is no competition for survival of existence between the parents and the children. Only the children participate. So this is lambda mu. I need to discuss it only two things from now. For now I need to discuss only two things. The first is how do we apply the recombination operator, and the second is how do we apply the mutation operator. Everything else goes intact, as we saw in the genetic algorithm and later in the genetic programming. It goes exactly the same, except for these two operators that we are to discuss now. The first one called as the recombination, and the second operator that is known as mutation. So we will touch upon the less interesting part of it, the recombination. In recombination, I'll assume that there are row number of parents. In genetic algorithm, we used to study crossover when we had only examples taking two children. Of course, the multi-parent was possible, but we only said that please generalize it. Here I'll be specifically taking the case where there are no parents, because the evolutionary strategies with low parents is more common. You need to specify how many parents group they participate in to generate in the child. So based on that, I got multiple forms in which the recombination can be applied. There are multiple mechanisms over which the recombination can be applied, and we will study some of them. The first, it's called as a no recombination. So I got in a population pool. I'll have gotten a population pool of no parents out over here. I have to select in child. So what the child does is that it randomly selects out which parent it needs to go in for. It selects out the parents and it copies all its attributes. So let me say it directly copies its attributes, and the child gets in the same attributes as the parent. It gets entirely the same characteristics as the parents had. And since it gets in attributes that the parents had, there is as a copy from the parents to generate in the child. So that's again a very simple kind of there's a very simple kind of recombination that can be applied. The other is called as a local intermediate recombination. This is what happens to be the local intermediate combination. Here also I got n parents. So a parent is nothing but of this format out over here. A parent is entirely of this format. How we generate in the children is something like a scattered crossover, wherein I select out random places where the characteristics will be copied. I select out the random attributes out of which the parents I select out the random points, I select out random attributes. So that's almost like a scattered crossover applied for a multiple parent algorithm. That's like almost random in nature. There is no predefined heuristics. Any parent will generate any attribute of any child, and the attributes will be copied as it is to generate in the child. So this is what I'll get in as my individual, I'll get in one of my individual. This one coming up from this, this second bit coming from this, the third one coming from this, the fourth one coming from the second parent, and so on. I'm assuming row to be 3. So there were 3 parents out over here. So this was what was the second kind of recombination that was possible. The other is known as a global recombination technique. The other is what is known as a global recombination technique. Here what we ultimately do is that we take in 2 parents. So suppose we say P1 and P2. We take in these 2 parents. In fact, there will be a P3, there will be a P row. We take in these row parents out over here, and what do we do is that we say that we'll take in a mean of all these parents to generate in the child. So for every parent xi, the jth attribute it is what generated the child. So I take in the ith parent, the jth attribute. So for every jth attribute generated in the child, I'll take in this arithmetic mean. I'll take in this mean, sometimes also taken as a weighted mean, and that is what generates my final individual out over here. Again, that is more or less the heuristic crossover that we are carrying out between two parents. Sometimes it's known as an intermediate recombination, wherein I take in two parents P1 and P2 and I generate my child, saying is that is ui times P1 plus 1 minus ui times P2, and ui can be anything. If it is 0.5, then that is nothing but arithmetic mean. That is where two parents, they have intermediate to each other, they generate in the child, and that is how this entire recombination takes place. So again, most of the fundamentals that we have out over here, most of the fundamentals that we study out over here, they are as this more or less copied from the general genetic algorithm part of it. They are more or less copied from the general genetic algorithm part of it. The other is called as lambda point recombination. Again, what do? We had some individuals, rather than copying attributes out over here, we divide them into some lambda parts by some lambda lines. So these are some lambda lines, so this becomes lambda plus 1 parts that these all are. Similarly, we'll divide in all the various parents. They may be internally divided into a set of attributes. So we'll divide them into lambda plus 1 parts, and then again anything comes up from anywhere in the children. Anything comes up from anywhere in this children, and that is how, after joining all these various parts, I get in my new solution. Now in this again we try to see that every part it contributes to some of the other child, as we have done in the crossover operator. So that places a restriction between the new children to be formed and the lambda, the number of parts that we are to be divided. And of course the children cannot be alike. These cannot be alike from an architectural point of view. They will not convey good characteristics. They will not lead to good characteristics. So these are the various ways in which ultimately what I need to do is that there are some parents, there are no number of parents, I need to apply some technique to generate the children, and what I wrote down was more or less general concepts of the general genetic algorithm. The only thing was generalized to the raw parents. That is important when we talk about these individuals out over here. The other important fact is that all these individuals, they contain not only the individual representation attributes but also the strategy parameters. So the strategy parameters, they also go recombination. So whenever children are generated from parents, there is an intermix of strategies. So strategies intermix to generate a new kind of strategy. So that's there intact. The other operator that is known as the mutation operator, that happens after we do some computations over all these strategy parameters, and we come up with the formal mutation rate and then apply this mutation over the individual. So this mechanism of how the mutation is applied, we'll see out in the next hour of study.